You don't have to go over that.
Okay, there you go. You see my apple full of coins?
Yeah.
So I asked my kids questions in class, and when they answer them right, I have little cubbies with their names, and I put the coins in their cubbies when they get the little answers right.
Are there pennies in it?
Yeah, there's pennies, quarters, nickels, everything. It doesn't matter. They're all, because they take them to the candy machine, the one by the front door, the crank one.
Yeah.
So, and that takes any coin. It doesn't matter what the coin is. So they just earn.
So you can show my pen trick?
Sure.
Hmm?
Yeah, you can show them the trick.
We got 2 pennies.
That's it.
What kind of fruit is that?
Fair.
That's right.
Here, you wanna show them the trick when they come, you can do that. There you go. Oh, do you want me to get you a glass of water or anything?
Yeah, good. Well, sound good.
Yeah, you gonna sit here?
Yeah.
All right.
Sit there.
Do you want ice or just water?
What?
Do you want ice or just water?
Just one.
Just water.
Like one.
Water. Water. Why? It's maybe 9:50. Water. Good for you. There you go. Can you reach it okay?
Yeah.
All right, good deal. Here they come. I hear them coming. Come the monsters.
That's water.
That's what I said, water.
I thought you said wine.
It's not. I'm not getting
That's all right.
wine.
That's all right.
Sweet girl, you have to pick a spot today. It's a little bit.
Howdy.
Daddy, this is Emma. This is Mr. Burke, my dad. Oh,
I do. Can you do this?
She tried. This.
I've been doing that for years.
There you go. Here come the rest.
Like, oh, yeah.
Yeah, he's big on hats.
Yeah, I always wear this hat.
Mm-hmm.
It's my signature hat.
There you go. He has a signature hat that he used to wear. He used to wear an Indiana Jones hat.
Oh.
And I was,
Look, still got him.
do you still have him? Hey, Eunice, come on in.
How you doing?
This is Eunice. This is my dad, Mr. Burke.
Come on
Oh yeah, I
in.
saw him in the email for lesson 22.
Yeah, he's hanging with us today. Yep. You're gonna do lab with us too. It'll be fun. He just flew in all the way from Virginia yesterday.
Yeah, and then airplane were.
Yeah, in an airplane. He flew first class, didn't you?
Yep,
Flew first class. It was nice.
I was in the front seat.
There you go. That's the way to do it.
Wow, I've never once flew on an airplane in my entire
You've not
life.
been on an airplane?
I've been in an airplane when I was visiting India.
Yeah, I was gonna say, you guys just got back from India last year, so that's a long flight. How long was that flight?
12 hours. First we went to India to Qatar and then from there.
To Qatar. Yeah, and then from there,
That
yeah.
was like 12 hours. And my dad's like, sleep.
Yeah, please, children, because you had all your younger sister and
Yeah.
everything, right? So yeah, you guys probably definitely wanted your kids sleeping. Well, Jason flew to Oregon yesterday, and that's a 5-hour flight. 23. Mm-hmm. Oregon's a long way. I've never been there, so
My dad's been to Washington.
yeah. I haven't been to Washington either. I haven't been up there in that corner. Closest I've gotten is California. Yeah.
Seems like I'm missing. Oh wait, no, it is.
I was gonna say, I can have an extra copy somewhere. You've got it now?
You sent something to the email that he likes he likes answering jokes.
He loves jokes. Yeah, Mr. Burt will tell many a joke today, I'm sure. You like jokes?
Can you tell me a joke, please?
Tell you a joke?
Yeah.
All right.
If it's
Got it.
appropriate.
Stood up in front of a judge for stealing a can of peaches. And the judge knew that the peaches had to be sliced to go in the can. He said, how many sliced peaches did you eat? He said, 14. For eating 14 sliced peaches, you gonna go to jail for 14 days. And his wife stood in the hall and they stole a can of peas too.
Because there's more peas in the can, right? Let me zip it down. There you go.
Thank you very much.
Yep, keep that horse in the barn, man. Bless you, Emma.
I can't believe he actually flew in the first class.
He did. He flew first class because he's got a little more room and he can spread out a little. And he had a good time. He's impressed with your first class.
Yeah.
Flying first class is pretty cool. Yep.
My dream is to fly in first class.
Oh yeah, he's living your dream, right?
Yeah.
Did you hear him? He said his dream is to fly first class. Yeah, it was good. He had a good time.
We can build a pinhole camera and we have to bring it on March 5th.
By the 5th, yeah. Mm-hmm.
It's gonna be pretty hard to do that.
Yeah,
I
you
saw
see?
a nice video on YouTube.
Yeah.
But we need to buy all the ingredients. We have some of them.
Yeah, there should be a lot of stuff you probably have hanging around, because like tape and glue and.
Definitely. We have low temp hot glue.
Yeah, I have that. Mm-hmm.
But high temp is way too dangerous.
It'll get you.
My sister, she's only 6 and she used a low temp hot glue and she got a bump on her finger.
It'll burn you, yeah.
Why do you use that? I told you many times not to use the low temp hot glue. It's dangerous for you. I have a friend that can't feel hot glue on her fingers and
Oh, wow. She's done it so many times. Nico and Carlos are running a bit behind.
And it's not lesson 24, it's lesson 23.
Oh, then I probably just have the wrong one.
You need 23?
You said lesson 24 instead of lesson 23.
No, I said 23. She said she could only find 24.
I think I have.
Look, even I have it. When I go to.
Do you need a copy?
For some reason they were out of order. So
Oh, no, what's it out of
Is
order?
it out of
There's
order?
23. That's lab 23. That's the right lab for today.
Wait a second.
Oh, that's mislabeled. You found it. That's what it is.
Oh, why does it say lesson?
Yeah, you found a brownie point and I just found one. Yeah.
you found it together. I probably wanted to.
You guys are silly.
I probably wouldn't have found that on my own because grammar is not my subject.
Grammar's.
I had a teacher for kindergarten, so yeah, I know all this.
I don't find, what, your mama or somebody else?
With my mom and
Yeah.
another teacher. I went to school in kindergarten.
Yeah, I can find other people's mistakes like this, but I don't see my own. Like when I write, I have a really hard time proofreading my own work. I miss stuff all the time. But I see everybody else's.
That makes sense because it looks right to you.
Well, it's not even that, it's that I know what I intended, and it's like when I read it, I see what I intended, not what I actually did.
Like one of those tricks where it has the same word.
Yes, like the or an or something that's real, a little word. Yeah, those are hard. Those are very hard to do.
Yeah, I found most of them like the and to.
Yeah,
And fine. You said big.
yeah, you found that one. And it's weird because it's like sometimes spell check is missing things that it should be getting, and I don't know why.
This is all what I do. as soon as as soon as you send the email, I just go to grammarly.com and type or like if it's too late, I just spend 30 minutes searching for
Look at you. You put my emails into Grammarly. He's got a trick
That's
for
like
you.
huh?
He's got a trick for you. You gonna show him your trick?
Yeah.
All right, here we go. Oops, you got it? Do you want your cane?
Now you can go home and do this to your parents. I got 2 pennies there.
Okay.
What kind of fruit do you see?
Orange,
No.
No,
an apple,
no,
pear.
a pear.
1, 2.
Oh,
Show that to your parents, they'll never catch it.
Yay.
that's fun. That's nice.
That's a good one. Weren't there other things too, Daddy? There was more than just that, wasn't there?
Oh, yeah. I have 5 pennies in the, I lay 3 pennies down.
You want 5?
You see any snakes there? Any snakes? There's 2 copperheads.
Yeah.
Two copperheads.
Oh.
Okay, you see any cops?
No.
There's 2 coppers.
See any police?
You see any cars?
No.
There's 2 Lincolns.
He's full of himself.
I didn't know there were so many wordplay jokes that you
Many jokes with pennies. Yes, many jokes with pennies.
I think he may be like like he has so many different jokes.
He has very many. Quite a few of them. Oh, we just interrupted class. Not appropriate.
We want to go random one. You do your lesson 23. Lesson 23. Magnetism.
Yeah, teach, silly.
He's interrupting the Spanish class.
Yep, just went right in. That's what he'll do. Yeah.
He's coming.
He's old and not quite there. All right. Well, I don't know where Darcy and Lewis are, and Nico and Carlos are a little bit late, but we'll go ahead and get started.
It's like 5 minutes or 10 minutes.
You're more like 15 minutes early. You're real early, always early.
It's the early bird.
Yep. So, okay, one thing real quick. The live streams are have been a little weird when they record. For the last 3 weeks, we've used the HDMI cable instead of casting, and for whatever reason, the Zoom recording has been of the video, not of the slides. So I'm trying a different setting today, and I'm hoping it will work, and I guess we'll find out. Okay, so we're doing magnetism, electromagnetism, and electricity today. Are we ready?
That's a mouthful.
Yeah, it is a mouthful. Y'all had a week off, so we should be good to go. All right, well, let's see. So we're going to talk about the nature of magnetism. Now, this next couple weeks, your lessons and the lab rats lessons don't quite align a little perfectly. So like when they're doing their big magnetism lesson is when we're going to do the compass lab. We're going to build a compass, and that's going to be really cool. So you're going to kind of float along through lab for the next couple weeks. I tried to make them line up as best I could, but it's just that your books are structured a little differently. Okay, so the nature of magnetism. All right, so what do we call the attraction of one magnet to another, Eunice?
Magnetism.
There you go. See a little. Do you have anything else? Any more? Yeah, magnetic force is the other word. But yes, magnetism is correct. You can call it magnetism or a magnetic force. Right. So what do we call the ends of a magnet, Emma?
Side.
Not sides that attract, they're on opposite ends. There's a positive and a negative. Do you know what we call those?
Plurality?
Poles, yes. Hey, hey, good morning. Y'all, we just started. We're on the first slide, so you're good. Y'all, this is Mr. Burt, my dad. This is Lewis. This is Lewis and Darcy.
Like that.
Yeah, he's gonna like hats. He loves hats. And we got two more boys. Nico and Carlos are running a bit late, but they're on the way.
Yesterday.
Did you see him yesterday?
Yeah, we were doing volleyball.
Ah, okay. So they should be here really soon. All right, so I'll let you grab your binders. Okay, so magnetic force or magnetism is the attraction of one magnet to another. Magnets have two poles or ends, which point in opposite directions, one north, one south. And the poles on a magnet align with the magnetic poles of Earth. So if I had a magnet and I just set it down somewhere, it's going to keep that north-south, even if I have it facing east to west. Does that make sense? We call one end north and we call one end south, and they will align. If it's a strong enough magnet, it will align with Earth's poles, right? But the little ones that you're probably used to, like the kind on your fridge or whatever, you can move those around because they're not as strong. So magnetic poles, which are alike, repel, and magnetic poles, which are unlike, attract. So the opposites attract, right? So a positive will attract a negative and a negative will attract a positive. You ever tried to take a magnet and two magnets and push them together and they push back? That's because you're pushing like poles toward each other, right? So that doesn't work. They won't do that. But if it's the opposites, they will snap together real fast, right? So magnets are surrounded by what? What do we call the thing around a magnet? All right, Lewis?
Magnetic field.
Yeah, a magnetic field. Okay. Magnetic field, which is a region of force they create. So a magnetic field can be mapped using, what do we call this? Do you know? When you draw out these lines? Do you know, Eunice?
Magnetic field lines?
Yeah, magnetic field lines, and sometimes you can call it magnetic field diagram. So it actually wraps around a magnet kind of like a sleeve almost, or like a really big donut. So it looks 2D there, like it looks like they're just making a circle on the sides, but really that goes all the way around the magnet. So if like my hand was a magnet like this, those lines are going to be wrapping all around it like this on the outside, like a sleeve.
Giant bracelet.
Like a big giant bracelet or a sleeve.
You
Or
don't know how
something.
to make a magnet?
Well, we're going to go through over that. We're going to talk about how to make magnets.
Okay.
Yep. So magnetic field lines spread out from one pole, curve around the magnet and return to the other pole, right? That's what we were just seeing. Okay, so inside of a magnet, making and destroying and breaking magnets. So here comes our making, what he was just saying. So when the electrons of the atoms which make up a magnet spin about their nuclei in alignment with each other, billions of atoms align and create a magnetic field or make up, do you know what we call it? Do you know it, Eunice?
Magnetic domain.
Yeah, magnetic domain. Okay, so basically, if you just have random atomic organization and you have some pulling one way and some pulling another way. Hello, boys. There's the rest of my class. Hi. Y'all, this is my daddy, Mr. Burt. This is Carlos and Nico.
Okay.
All right, so we're only on like slide 3, so you're good. All right, so what happens is all those positives and negatives are dealing with each other so much and interacting that eventually they'll all align like that. And when they all align, that's what makes something magnetic. So in a magnetized material, all or most of the domains are arranged in the same direction. Okay, that's what makes something magnetized, when those domains are all in the same direction. So what do you call, it says blank are those which form strong magnetic fields. Do you know what we call these materials? They contemporarily possess magnetic qualities. Do you know?
Ferromagnetic material.
Yeah, okay, ferromagnetic. All right, this is a Latin and Greek root moment. You know what magnetic means because we just talked about it. F-E-R-R-O, pharaoh. Does that sound like anything? Not pharaoh like an Egyptian pharaoh because it's not PH. It's F-E-R-R-O. Does that sound familiar? Anybody ever seen that anywhere? Okay, I'm going to show you something I've been hiding. I've been hiding it from you. This is called ferrofluid. Anybody ever seen ferrofluid before? Okay. FER is a Latin root for iron. Okay, so if you look at iron on the periodic table, its symbol is Fe. All right. This is ferrofluid. So it's a fluid that contains tiny particles of iron. And when I touch, let me turn it this way so you can see it. This magnet
Oh, I have
to
seen
the
that stuff.
outside, you see how it does that? And it, as you back it up and get it closer, it'll make very specific shapes. And that has to do with the way those magnetic domains within the particles are aligned. And it'll make almost like it makes predictable patterns. But the crazy thing is, like, if I shake it up, and now it's like all these little tiny bits, I can get them to whoop right back together. And I can even, this is cool, can you see? Even put this guy on the other side and I can shift it back and forth.
That's so sad.
Isn't it neat? That's so fun. So I'll pass this around, but it's glass, so be very careful. And the magnets, also, if you bang them together too hard, like that, like I just did, they're starting to chip. So we need to be real careful with them. So just be very careful as you move it around, and I'll pass it around so you guys can all see it and just kind of play with it for a minute before you share. Yeah, look, there's the other magnet. So that's ferrofluid. So ferro, anytime you see FER, that's dealing with iron. All right, so ferromagnetic usually implies it's something metallic. Okay, so what is the material? What do you call the material that keeps its magnetic properties? It's not just like temporary, but it stays magnetic. Do you know, Nico?
Permanent magnet?
A permanent magnet. Okay, so those things that Emma has right now that she's playing with the ferrofluid are permanent magnets. So some things are only magnetic temporarily, sometimes for a fraction of a second. Other things stay magnetic, like the magnets on your fridge or whatever. Those are permanent magnets. All right, now let's watch this quick little bit on magnets. This guy is dressed like a Roman centurion or whatever. You know Marvin the Martian? He looks like that.
If you take a piece of wood and put it next to another piece of wood, nothing happens. And if you take a piece of granite and put it next to another rock, still nothing. But if you take this piece of iron and put it next to this other piece of iron, magnet. Magnetic objects are able to magically attract at long distances because they generate magnetic fields that extend invisibly out beyond the object. But the mystery is this: where do magnetic fields come from?
Well, that's easy, Henry. We've known for a long time that electricity and magnetism are really just two sides of the same coin. Kind of like mass and energy or time and space. They can be transformed into one another. And in fact, a magnetic field is just what an electric field becomes when an electrically charged object starts moving.
That makes sense for explaining why a current of electrons flowing through a wire causes this compass needle to move, or how currents in the Earth's outer core generate the geomagnetic field. But a bar magnet or the compass needle itself are just pieces of metal without any electrical current running through them.
Or are they? At the microscopic level, there are loads of electrons whizzing around the atoms and molecules that make up any solid.
Right. This brings up an excellent point. The magnetic behavior of any everyday object is influenced by a fascinating combination of effects ranging from the level of particles to atoms, collections of atoms, and collections of atoms. First, individual particles. Unlike the everyday workings of gravity and electricity, permanent magnets can only be fully understood as a quantum mechanical effect, in much the same way that particles like electrons and quarks have fundamental properties called mass and electrical charge. Most particles also have another intrinsic property called tiny magnet. Just kidding, it's called intrinsic magnetic moment.
Tiny
But
magnet.
really, that's just technical mumbo jumbo saying that particles with electric charge also happen to be tiny magnets.
If you want to know why they're tiny magnets, well, you may as well ask, why are particles charged in the first place? Or why do objects with mass and energy attract each other gravitationally? No one knows. We just know that's the way the universe works.
Exactly, and since the 1920s, we've known that each individual electron or proton is basically a tiny magnet, which brings us to the level of atoms. An atom is a bunch of positively charged protons with a bunch of negatively charged electrons whizzing around them. The proton tiny magnets are about 1,000 times weaker than the electron ones, so the nucleus of the atom has almost no effect on the magnetism of the atom as a whole.
And you might think that since many, though not all, of the electrons are also moving, that like a current in a wire, they should generate magnetic fields due to that motion. And indeed they do. These are called orbital magnetic fields.
Except these don't usually contribute to the magnetic field of an atom. Here's why. Electrons in atoms are accurately and complicatedly described by quantum mechanics, but the gist of the story is that electrons congregate in shells around the nucleus. The electrons in any filled shell zoom equally in all directions, so the currents they generate cancel out and generate no magnetic field. These electrons also come in pairs whose tiny magnets point in opposite directions and also cancel. However, in a half-filled shell, all of the electrons are unpaired, and their tiny magnets point in the same direction and add up, meaning that it's the intrinsic magnetism of the electrons in the outer shell that gives an atom the majority of its magnetic field. So atoms near the side of any of the major blocks of the periodic table, which have full or nearly full outer electron shells, aren't magnetic, and atoms in the middle of the blocks have half-full outer electron shells and are magnetic. For example, nickel, cobalt, iron, manganese, chromium, etc.
Wait, but chromium isn't magnetic.
Ah, but just because an atom is magnetic doesn't mean that a material made up of lots of that atom will be magnetic, which brings us to the level of crystals. When a bunch of magnetic atoms get together to make a solid, they generally have two options. One is for all the atoms to align their magnetic fields with each other, or they can align their magnetic fields in an alternating fashion so they all cancel out. The atoms will do whichever one requires less energy.
That's why chromium, for example, is a very magnetic atom, but a very unmagnetic solid, because it's one of the most anti-ferromagnetic materials that we know. Iron, on the other hand, is the namesake of ferromagnetism, so it is unsurprisingly ferromagnetic, or in usual parlance, magnetic.
Sometimes. The last and final level of magnetism is that of domains. Essentially, even in a magnetic material where the magnetic fields of atoms line up together, it's possible that one chunk of the material will have all its atoms lined up pointing one way, and another chunk will have all its atoms pointing another way, and so on.
All of these domains are of similar size, then none may be strong enough to force the others to align with it. In which case, a piece of iron, for example, may have no magnetic field at all because of all the warring magnetic kingdoms.
However, if you apply a strong enough magnetic field from outside the material, you can help one domain expand its control over its neighbors, and so on, until all of the domains have been unified into one kingdom, all pointing in the same direction.
And now, finally, you can rule with an iron fist. I mean, magnet. It's magnetic because it's ferromagnetic and all of the domains are aligned.
Exactly. What's remarkable is that magnetism is a fundamentally quantum property amplified to the sides of everyday objects. Every permanent magnet is a reminder that quantum mechanics underlies our universe. In order for an everyday object to be magnetic, though, it has to have a unified kingdom of magnetic domains, each made up of bajillions of magnetic atoms which also need to be aligned with each other, each of which can only be magnetic in the first place if it has an approximately half-filled outer shell of electrons, so their intrinsic magnetic fields can align and not cancel each other out. Not surprisingly, these criteria are pretty difficult to fulfill, which is why there are only a limited number of suitable materials you can use when you're building a magnet.
Or you could just run a current through any electrical conductor and produce a magnetic field that way.
But hey, why does that work in the first place? Click here to go over to Veritasium and we'll find.
So, clear as mud, a little bit. So when all those domains align, that's when you get a permanent magnet. So there are plenty of elements in which the atoms are magnetic, but the whole chunk of material isn't. It has to do with how those atoms are aligned within that chunk of material. So Earth, all right, Earth's a giant magnet, right? Earth as a magnet and magnetic declination. Oh, there's a good word. So what are the things that form strong magnetic fields with Earth? What have we got? Do you have it? Anybody? All right, Eunice, what you got?
Compass.
No, we're looking for the ferromagnetic materials again. Okay, so again, the ferromagnetic materials are those which form strong magnetic fields. Some materials can, like we said, temporarily possess magnetic qualities, but not constantly. They can be made magnetic for a period of time. So what's a material that keeps its magnetic qualities? We already said it was a permanent magnet. All right, now, navigators, especially the guys like way back in the day in their ships, right? Navigators take advantage of Earth's magnetic field by using, now Darcy, a compass, right, okay. So they use a compass, which is a device with a freely spinning needle, which usually points north to find their way. So why in the world does that work? Why is it Why does that work? Why is that little needle point north? Who can tell me? Anybody tell me? Can you tell me?
Because of the magnetic field of the earth.
Yeah, the magnetic field of the earth is really strong, but we don't notice it because we live in it. And compared to other things, it's maybe not as strong. It's not strong enough to like turn big magnets, but a little tiny needle that's floating on water or that's on a very, very flexible little axis can spin. And we're actually in 2 weeks from now, we're going to make a compass that can float on water, and you'll watch it. It will turn north. It'll be pretty cool. All right. So is somebody clicking? Tapping the telegraph, sorry. All right. So who was it that suggested a compass's behavior was due to Earth being a big magnet way back in the 1500s? Do you know who said it? Who's it?
No idea.
No idea? Nobody wants to guess over there? Eunice, you want to guess?
Sir William Gilbert.
There you go. Sir William Gilbert. So this is a dude back in the 1500s, guys. We were just barely, Europeans had just barely discovered North America. So this is the time when a lot of people were doing a lot of traveling in big, giant wind sailing ships, right? And they were using compasses to guide their way, but they didn't really understand how they worked. But this guy's like, I think they work because Earth's a giant magnet. Okay, so Earth has this immense magnetic field surrounding it, just as there is a magnetic field around a bar magnet. So remember we said it was like a sleeve around a bar magnet? Earth has that too, and it goes way, way, way out, right? Now, click. Earth's geographic North Pole, the one that's on maps, isn't the same as Earth's magnetic North Pole. The difference between these is known as what? Do you know what the difference between geographic and magnetic North Pole is called? Darcy, do you know? You were thinking about a hand?
The
Mm,
magnetic North Pole and the magnetic.
yeah, what do you call the difference? Lewis, what do you call it?
Earth's geographic North Pole, the Mars one, the map is the same thing.
Right.
Magnetic
Declination, magnetic declination. Okay, so look right here. This is the top of the Earth. All right, that is magnetic North Pole. That's geographic North Pole, right there in the middle. That's where we say, oh, Santa lives at the North Pole, right there. Bing. Okay, but that blue asterisk, that's the magnetic North Pole. So we know, and we know that over time that has shifted, right? How do we know that it's shifted? You know? Yeah, okay, so the North Pole, currently this is north, right? And this is south, right? But it wasn't always that way. Sometimes this was north and this was south.
Oh.
Earth didn't do this. So what happened? How do we know that happened? Do you remember? Think back to the very beginning of the year. We did that little bit of earth science. You remember? Okay.
Tectonic plates.
Yes, it has to do with tectonic plates. Yes. Okay. So right at the middle, right here. What's right here in the middle of the ocean?
The equator.
The equator's this way. Yeah, there are tectonic plates there. So you've got the mid. Yes. Okay. You have the mid-Atlantic ridge right here, right? This plate is moving this direction, and this plate is moving this direction, right? They're divergent plates. They're moving in opposite directions. Remember, you have magma coming up like this, welling out. So as that magma comes up and it wells out, the rocks that it forms that have iron particles in them, right? It's coming up and iron particles are in them. Those iron particles are aligning with the poles. Now, you remember Alfred Wegener? He was the dude that was working during the military in the war. He was sonar scanning the bottom of the ocean, and he was using all kinds of equipment. And he found striping on the ocean floor that showed all the irons pointing this way, and then all this iron's pointing this way, and it was like this, and then this, and then this, and they were mirror image. And remember, that's how we prove that there is continental drift, there is tectonic plate motion, it's a real thing, and we can prove it because you can see it. So Earth's magnetic field affects the movements of electrically charged particles in space. Charged particles also affect Earth's magnetic field. So far above Earth's surface, there are two donut-shaped regions of charged particles traveling at very high speeds. What do we call these? Do you remember, Emma? No. It's named after somebody. Ooh, Nico's looking. What you got, Nico? Van Allen belts. Okay. These are Van Allen belts. All right. So these fly around the outside of the Earth and it's got charged particles and they're whipping all around. So also in space are what? What you got, Eunice?
Solar winds.
Solar winds, which are streams of charged particles flowing from the sun. They shape Earth's, what do we call this region of Earth? Yeah, Darcy. Magnetosphere. Okay, the magnetosphere is what you call that big sleeve around the Earth. Okay, that's the magnetosphere. All right, very good. Now, since Earth produces strong magnetic field, Earth itself can make magnets. Okay, so when Mr. Burt said, you know how to make a magnet? So Earth can make magnets and we can make magnets. So the record of Earth's magnetic pole reversals can be seen at the mid-ocean ridges, which is what we just talked about. Okay, let's watch this one real quick and he's going to explain Earth's magnetic field a little better for us. Ooh, let's travel the universe. Okay.
No one has ever taken the journey deep down to the heart of our planet, but by studying the way shock waves from earthquakes
I think he's Russian.
travel through the planet, scientists have worked out its likely structure. So now we know that our planet's magnetic field is generated deep down in the Earth's core. Earth's magnetic field is caused by a dynamo effect. The outer core of Earth is a liquid metal. Fluid motion there generates electric currents. The motion of the fluid is sustained by convection and driven by buoyancy. The Earth spins on its axis. It makes the electric currents to form a magnetic field that extends around the planet. If the mass of the Earth was solid, there wouldn't be as much of an electric field. A similar example of the dynamo effect is the dynamo light on a bike. Out of the bike, magnets in the dynamo start spinning, therefore creating an electric current which turns on the light. Did you know Earth's magnetic field is 3.5 billion years old, and since then it has shielded every life form on Earth from the sun's harmful cosmic radiation.
So since we have the magnetosphere, it's protecting us from radiation, which is good, right? Anybody have a dynamo on their bike? So it's one of those little lights that lights up when you pedal. So we're actually going to be playing with the dynamo in a couple weeks. We're going to bring it out like a demo and give everybody a turn. When we're doing AC and DC power, we'll have the dynamo out and you can switch it from AC to DC power and turn this little crank and it'll cause a light bulb to go off. And it's pretty cool.
That music was very.
It was relaxing spa music and a Russian dude was very relaxing. All right. So electric current, magnetic fields. Let's wrap this up. So moving charge and magnetism. All matter is composed of atoms, and atoms are composed of subatomic particles, which are protons, neutrons, and electrons. What kind of charge okay, so electrons and protons have let's just say electric charge. Electrons are what? Positive or negative? Negative. Electrons are negative, and protons are positive. It starts with a P, so you can remember it's positive. Neutrons. What charge do neutrons have?
They're
Anybody know?
positive or negative.
They have no charge, right? They're neutral. Neutrons are neutral. Protons are positive. Electrons are negative. So when you're looking at an atom, you've got your protons and your neutrons in the middle of the atom, and then you have your electrons that are whizzing around the outside. Now we're going to do a little bit of chemistry at the end of this class before we start next year's chemistry. And we're going to make some models with Skittles or M&Ms where you can make it. But there isn't really a way to model an atom with physical material that makes sense. Like we can't really show all the activity, so we can just get kind of close. So if you've seen the models where it's like, you know, I don't know, I thought there was one somewhere on my desk, but if you see them have like the little rings that go around, like that's just our conceptual diagram. So when an electric charge flows through a material, it creates what, Emma?
A magnetic field.
Yes, a magnetic field or electric current, sorry, electric current, which will create a magnetic field. We'll get there in a second. So an electric current produces the magnetic field. So when you have electrons moving, you have an electrical current, and an electrical current creates a magnetic field. All right, so conductors, insulators, and resistance. So what do you call a complete path through which a electric charge can flow, Darcy?
A insulator.
No, look, a complete path through which an electron can flow. Yeah, you're close, Emma.
A circuit.
A circuit, that's what we're looking for. Okay, a circuit. So a circuit is a complete path through which an electric charge can flow. In I think next week or the week after, I'm gonna give you a worksheet that you're gonna do in class that's got it's got a circuit diagram and it's got light bulbs on it. And it tells you which light bulbs are out, and you have to determine like how the electricity is gonna flow. Like where is it not gonna go and where is it gonna go? Yes.
I wish I brought it here today, but I made this really cool robot
Oh,
at RDO's.
yeah.
And it's so cool. And it moves this way
Uh-huh.
and it moves this way.
You'll have to bring it next week and let's have a look at it.
It might be something else next week because
Oh.
we use the same material.
Oh, I see what you mean. Okay.
So, but I'll bring whatever we make this week next week if it's done.
Okay. So first, you have a circuit as a source of electrical energy. Second, you have circuits have devices that run by electrical energy. And third, electric circuits are connected by conducting wires and a switch. So what do you call a material through which an electric charge can easily flow? What do you call those materials that can let an electric charge flow through them real easy? Bye. See you next week.
Nice to meet you.
See you next week. Love ya. Te amo. What?
A conductor.
A conductor. Okay, great. So conductor is a good material through which electricity can flow, right? Excellent. So copper is probably one of the best conductors. And copper's actually gotten very expensive. And do you know that if there are neighborhoods where they're building houses, and sometimes like when they're under construction, like you can just kind of walk through them, you know, because there's no doors yet or whatever, people steal copper piping and wires out of houses because it's very expensive right now. And your pennies are not copper all the way through. They're only copper on the very outside. The middle is filled with nickel because copper's very expensive now. Didn't used to be, but it is. All right, so that's copper. In a conductor, some of the electrons are only loosely bound to their atoms. Okay, so think about this. If you have a material and the electrons there's a lot, remember it said with magnetic materials, you have to have, it's okay, like a half full shell. That has to do with how far away from the center those electrons are. Okay, so if you have some electrons that are on the very outside of your atom and they're not held real tight to the center, then they can move. So you get the electric charge. It's not like you have one electron that's just moving. It's just that charge can flow through that material because all those electrons are kind of flexible, right? All right. So what do you call something that doesn't carry electric charge well? Nico?
Insulator.
An insulator. Okay. So if you look at any of the cables in your house, any of the plugs in your house, they're usually covered in like a rubber or a plastic. That's because those materials have their electrons bound very tightly to them and they do not conduct well, right? So does water conduct electricity?
No.
It does, but you know what makes it conduct it even better?
Electricity.
Putting salts in it.
Salt.
Because then there are free ions, which are extra electrons, right? And now you've got all these free electrons moving and you can make it conduct better.
So like a pool that
Mhm.
uses salt.
Yes.
Would be clean, would be very.
Very much so, a much stronger conductor. Okay, so electrons in an insulator are bound tightly to their atoms and do not easily flow. So what do you call something that interferes with the flow of charges? All right, Eunice?
Resistor.
A resistor, okay. Resistor interferes with the flow of charges. So say you have a lot of charges coming really strong and you need to slow it down or resist that flow. That's when you'd use a resistor. The opposition to the flow of charge is called what? Goes with resistor. You know, Eunice?
Resistance.
Resistance. So resistors produce resistance. Duh. Right? Okay. So on the other hand, a material which has little or no resistance, what do we call that?
A superconductor.
Yes. Okay. So you have conductors and then you have superconductors and you have insulators and you have resistors, right? So you can think of resistors kind of as lumped with insulators and superconductors with. Y'all don't tap the telegraph right now, please. Thank you. So anyway. You have all that going on. So you ever taken apart something electronic and seen this circuit board? You ever done that?
Yeah.
Yeah, it's crazy, right? You see all that? Oh yeah, you've done that with your Nintendo? Well, you can see that, like all these little things in there. All right, so these are resistors, all right? If you ever see one of these, yeah, they look like little pills a lot of the time, little tiny capsules, right? And they have color codes, and those color codes are what electricians or electrical engineers are going to use to determine how much they multiply or tolerate or resist. And so all those little stripes that you see on resistors are there for a reason. Now, do you remember a couple weeks ago when we were talking about color and color blindness? This is why electricians cannot be colorblind to any of these part of the spectrum, because that causes an issue, obviously, right? You have to be able to see these colors if you're an electrician.
Oh yeah, because you have to like cut the
Right, yeah, and cut the right wire, use the right semiconductor, use the right resistor. All right, so we're gonna play this game real quick. Conductor or insulator? Let's see what we think. All right.
Do you think this dill pickle is a conductor or an insulator?
insulator.
What do you think?
Cup of water. Welcome to Moon Math and Science. And is it a conductor or insulator? A conductor is an object or material that allows the flow of negatively charged electrons in one or more direction, which results in electric current. An electrical insulator is a material in which the electrons do not flow freely. What we will do
We're
in
keeping him
this
up.
video is take a look at some different objects. We have some metals, some plastics, a Sharpie, how about a pickle and some water. We will hook it up to some electricity and see if it is a conductor or an insulator. Up first, we have a copper. Hook it up and yes, it's a conductor.
Turned on the light.
How about this piece of plastic?
What do you think?
Flip the switch,
Mhm.
nothing happens.
Insulator.
It is going to be an insulator. Now we move on to another piece of metal. It's aluminum.
Aluminum. What do you think?
And yes,
Yes, it's a conductor.
it's
Yeah, conductor.
Then a
now
conductor.
how about some wood?
Insulator.
Yeah.
Insulator.
Insulator. Very good.
The switch, nothing happens. So it is an insulator. After the block of wood, let's try a different. How about we try a Sharpie? It's plastic.
What do we think?
It's hooked up. We go to the switch and nothing happens.
Insulator.
Insulator. How about this? Let's try some water. I've got two nails hooked in
What do you think?
with the switch.
Insulator.
Nothing.
Insulator.
Well,
Insulator.
let's modify the water slightly. Let's add some salt. As I add the salt, I pour it in, I go back to the switch. What do you think? Is it gonna change? I hit the switch, and yes, it is now a conductor.
Just like
Salt
that.
allows the electrons to move. Next, let's try this screwdriver. The reason why I use this, I have plastic on one end, metal on the other. I flip the switch, nothing's happening.
Yep.
But now, if I move it to where it is touching metal only, it's now a conductor.
Right.
The plastic helps insulate it. How about this? How about the pickle? It has a lot of salt in it.
What do you think?
That, I plug it in, it smokes a lot, it glows, but I would consider it an insulator.
I wanted the pickle to
What about
conduct.
celery? It tastes salty, maybe it has enough salt in there.
What do we think about celery?
Well, you can see for yourself. Nothing really happens. Well, it does start smoking a little bit.
Smoking celery.
Celery with
Gross.
and bolts going through it. Smoking, but it is an insulator.
If you do anything with a vegetable.
Next, how about the apple? Kind of a dud. Well, not really. It's an insulator. So if you need to insulate an apple, it is your object.
That's funny. What an idea.
So I hope that helps. If you, it will help.
I have this kind of thing, like if you take a wire and
You-
put it into copper, the light will get on.
All right, so this last bit, electromagnets. All right. So solenoids and multiplying magnets. A familiar electromagnet is what? It has a current carrying coil of wire, which can be found as part of a car starting mechanism. Oh, is that your hand, Carlos, or you're just playing with that? Darcy.
A solenoid?
A solenoid. Okay. A solenoid with a ferromagnetic core. What do we call that one? All right, Eunice?
Electromagnetic.
It is an electromagnet. Yep. Okay. A solenoid is in your car. If you have an older car, especially, it's really easy to see. And you can use a solenoid as part of the starting mechanism of your car. Basically, that electromagnet will move in such a way that it allows an electrical connection to be complete from your battery.
Is that how people hotwire cars?
It's a little different, but there is a way to start a car by, if your solenoid's dead, there's a way to start it, and I can show you that too. So an electromagnet is a strong magnet which can be turned off, basically. Okay, this is the starter motor. I'm going to come back to it in just a minute, okay? Oh, no, I'm not. That's the last slide. Okay, here's how your solenoid works. It'll show you.
The initial key is turn. It causes a small current of electricity to flow into the solenoid coil.
So this is
The
in a
solenoid
car.
is usually made of two coils, known as the pull-in coil and the hold-in coil. The end of the holding coil connects to the casing of the starter motor. So the current returns to the battery by the frame of the car. The pull-in coil is connected to the main output terminal. Both coils are energized to create a strong magnetic field. This pulls the piston back, and as the contactor plate connects across the main terminals, both ends of the pulling coil will become the same voltage. There will be no voltage difference across this coil at that point in time, so the coil will turn off because there's no current flowing through it. It takes far less energy to hold the piston in position, so the hold-in coil continues to run. As the piston moves back, it's going to pull on the lever. This pivots and transfers the motion to the drive sleeve, pushing it forwards. As it moves forwards, it slightly rotates the pinion, allowing it to lock the wheels in the clutch and slide the pinion into the flywheel. As the contactor plate connects across the terminals and turns the pull-in coil off, a very large current will now flow through the contactor plate, through the thick wire, and into the brushes. From here, it flows to the commutator plates and through the coil, then back to another commutator plate and through another brush, which is grounded to the frame of the car. So the current returns to the battery. The coil produces an electromagnetic field, which interacts with the permanent magnet or field winding in the stator. This interaction causes the rotor or armature to rotate very fast with a high torque. The rotor transfers this through the shaft, through the clutch, and into the pinion gear, which turns the flywheel. As the flywheel starts the combustion process, the engine will eventually begin to rotate the flywheel faster than the starter motor. This unlocks the overrunning clutch, so the pinion gear spins freely. When the key is released, it cuts the power to the solenoid coil, which releases the piston. The spring pushes the lever back, removing the pinion gear from the flywheel. The current is cut through the starter motor. The combustion engine continues to run by itself, and the alternator recharges the battery. We have also covered how the car battery works in detail previously, I'll leave a link for you in the video description down below. Check out these videos to continue learning about.
So I will put in your resources a video of a way to bypass that process in your car where you can create a new circuit with a screwdriver and make your car start even if your starter isn't working. Have you ever been in a car where the battery's dead and you turn the key and all you hear is click, 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 click?
In the middle of Savannah,
Ah,
in the middle of the highway.
that click, click is the electromagnet moving. Click, click. That's what you're hearing. So it's not enough battery to get your car moving, but you have enough charge there in your starter system that'll get the little electromagnet to click, 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 click. Sometimes people turn it and it goes, brrr. You ever heard that? And it doesn't turn over, it just kind of rattles. That's what that is. So yeah. All right. One quick note before we shift over to lab in a second. And
Something but a cell phone.
oh yeah, go ahead.
In old cars. And I've seen people hook up selling and they get off by put a new solenoid and it doesn't work. That solenoid's got 2 screws in it. 2 holes in it, you're supposed to bolt to the front, to the car, but then it works. It's gotta be grounded.
Mm-hmm.
If it's sitting in there, it don't happen.
That's right. That's right. This man knows everything there is to know about cars. Everything.
I got Rapid in here. He wants to be.
Yeah?
He wants to be a mechanic one.
Well, he should come hang with this dude because he would do it. Well, Cole, Cole loves cars. So one more thing I want to say before we move to lab. All right. So it is the 19th, 20th. It is the 20th. How many-
days after my birthday.
Oh, happy birthday, Louis.
Mine 12 now.
How old are you now?
12.
12. Woo! All right. The big 12. All right. How many more days are left in this month?
Eight, nine.
It's a leap year, 9 more days. Okay. If you haven't already re-enrolled for next year, you have 9 more days where your space is saved. On March 1st, it opens up to the whole world. And I can't promise there are spots after that. So if you plan on coming back next year, get in the next 9 days. Just go in, hit the little enrollment deposit thing. It's a $25 enrollment deposit. If that's an issue, let me know. Like if you can't swing that this month, let me know. I want your name in my list, okay? Because I hope everybody comes back. I would love to see everybody back next year. But we have to make sure that we save your spot. And I can only save it for 9 more days, okay? Everybody gets that? 9 more days, and then I can't save yours. All right. Any questions about today's lesson before we move to lab? Okay, let me see, Nico, let me have my glass and my magnets back over here.
Those come together. Wait.
They're fun, right?
Danny, can I show you something that I discovered?
With this?
Yes.
Yeah, show me real quick.
That I can make the thing jump to the next other
Okay,
side.
she's figured something out. Can you do it on the table? Because your leggings are black and it's hard to see. There we go. Oh, look at that. You're throwing it from side to side. That's very cool. Yeah. Excellent.
It's hard not to get them to click together so.
I know.
Danny,
Did you want to see it? It's pretty cool. Yes, sir. What you need?
is Mr. Britt gonna stay for next week?
No, Mr. Burt will be back in Virginia on Saturday afternoon, but he is here for now.
A couple things they.
He's gonna show you something first.
Just put that on.